Hello, I would like to start by thanking you all for coming, and especially Johan for this opportunity to meet a community of people open to new ideas in interdisciplinary science. So I will talk about Finsler Spacetimes, observers, and the applications of this new type of geometry, which may be surprising. There is a wider range of applications, as we will see. But this will be the structure of my talk. First, I will talk about the basic foundations of this Finsler geometry from the viewpoint of observers. Then, as I said, I will discuss the different applications, and in the end, I will give you the main references. So, okay, what are observers? Well, observers are anything that can measure, say, for example, space, which we call x, and time, which we call t. But then relativity theory comes and says that if now we have a different observer, then they will measure some different space x prime and some different time t prime. So what's relativity theory saying? Is it saying that everything is relative? And then is it saying that there is no objective reality? Well, not quite. Because if, for example, the second observer O prime is moving with respect to the first one along the x-axis with some speed v, then the theory says that there is a very precise relation between the space and time measured by the second observer and the space and time measured by the first observer. And the relation is precisely this one, which includes this factor gamma depending on the velocity. And this is called a Lorentz transformation, which were around by different authors really before the birth of relativity theory by Einstein. But beyond details, the important thing is that here there is the measurements are different between the different observers, but still there is a very precise relation between the two measurements. And in this sense, the measurements are still coherent. This is more easily visualized with geometry. If we draw a so-called space-time diagram with space on the horizontal axis x and time on the vertical axis t, and if we draw the so-called, what we call the space-time velocity of the different observers. If we draw them, we will see that they lie in this yellow hyperbola, okay? And then what are we saying? So if the red vector is the space-time velocity of the first observer and the blue vector is the space-time velocity of the second observer, then this Lorentz transformation that we just saw corresponds to a very simple geometric thing. It's just a hyperbolic rotation along the hyperbola. It is a hyperbolic rotation in such a way that now O prime becomes the new 0, 1 vector. Okay, so it has a very geometric form with hyperbolic cosines and sines. And the important thing about viewing this geometrically is that now we realize that these rotations, these geometric transformations, live invariant a quadratic form, precisely this quadratic form here. So if one takes displacements in space to the square power minus displacements in time to a square power, this quantity, this quadratic form, stays invariant. And in this manner, this is one can think that this is the objective quantity that describes space-time. So from the geometric view, we have arrived at an invariant, at an objective quantity for all observers, which is the basis for space-time geometry. But okay, this is special relativity, and this is really the simplest case. It's highly ideal. Why? Well, because of many things. But for example, think about what may be the biggest problem in fundamental physics, which is unifying general relativity with quantum physics. Then one realizes that the presence of matter introduces some anisotropies between space-time directions. So in other words, because of the presence of matter, different space-time directions may not behave the same. And this might be especially important at the Planck scales. But then notice the important geometric consequence. If this is true, and we now consider the transformations between the measurements of the observers, Now we realize that these transformations, call them F, for example, they cannot be Lorentz transformations in general. And why they cannot be Lorentz transformations? Well, because if they were, Lorentz transformations connect any direction with any other direction. But we are saying that there is anisotropy, so the directions do not behave the same. It's impossible in general to connect any direction with any other, and in this way it is impossible that the relation is a Lorentz transformation in general. Now, if we take this to be true, at the end of the day, the most important consequence is that because we do not have Lorentz transformations now, this quadratic form will not stay invariant any longer. So, in other words, Lorentz symmetry is violated. And for a detailed account of how this happens, I have given you the brief version. I refer you to this paper by Bernal, Javaloches, and Sanchez. But yeah, the important consequence is the violation of this quadratic form. So now what do we do? What's the approach now? One can take many approaches now, but here we will take the approach of Finsler geometry. What is it? Well, in Finsler geometry, we postulate the existence of some invariant which may not be this simple quadratic form. It must be, in general, something more complicated. We postulate the existence of an invariant quantity L, which depends on the space-time point P, and also on the space-time direction V. And this invariant, okay, we postulate that it exists, and we will call it a Lorentz-Finsler metric. So in this way, we still have a quantity that is objective, describing space-time. So this allows for measurements of proper times and distance by different observers. The difference with before is that now we do not specify of what type are the transformations between the different observers. So that's the main freedom of this geometry. That's the main freedom of this theory. That now the transformations between the different observers, we left them unspecified. There may be some transformations. We just give total freedom to what those transformations are exactly. But still, we have some invariant and objective quantity. And geometrically, this is also very pictorial because this means that the previous hyperbola that we saw is now deformed to this set here, corresponding to the directions where L equals -1. And the previous light cone, okay, I have not paid much attention to the light cone, but the light cone here was these two lines at 45 degrees. Now this light cone is also deformed to this set here of directions where L equals 0. And let me just point out that indeed this approach has been applied to approach quantum gravity phenomenology. So the questions that I mentioned before are really approached by this type of geometry by different authors. But again, coming back to the geometry, the thing is that the elements that we saw before are now deformed, and here you can say you can see a possible deformation of the hyperbola. Okay, there may be many more possible deformations, but this is just a simple example of how we could deform the hyperbola in a Finslerian way. And this is a way in which we could deform, for example, the light cone. And here I have depicted this in 3D to highlight the most important phenomena, which maybe the most important thing is that these cones, these deformed cones, now they are not round, let's say. They are not round in the sense that if one cuts them by hyperplanes, what one obtains is, in general, not an ellipse. Before, in the round cones, you could only obtain ellipses, but now, in these deformed cones, when you cut them by hyperplanes, you will get, in general, just any convex curve, but not necessarily an ellipse. So there is much more freedom, yeah. And for example, you may think of the shapes generated by the superformula, which is very general. One can realize that in Finsler geometry, as long as this shape is closed and contains the origin of the hyperplane, yeah, this would be allowed. This would be allowed in Finsler geometry as the shape of these deformed cones. So it's a very, very general geometry. There's a lot of freedom, and because of this, one hopes to be able to model many more phenomena that one wasn't able to model before. So with this invariant quantity L, we define a Finsler spacetime. Here I will be just a bit technical for a moment. We write G mu nu, which depends on P and V for this quantity here, which is just the Hessian of L with respect to the direction variables. And I put this here only to point out that the classical case, which is Lorentzian geometry, as in Einstein's relativity, is precisely the case in which this object does not depend on the direction. Or equivalently, it is the case in which L gets this quadratic expression here. This is just to compare with the classical case. So, okay, as comparing with the classical case, you still see the freedom that we have, the huge freedom that we have. But okay, even though we are generalizing, we will still take the main lesson from general relativity. What is it? The main lesson from general relativity is that gravity is really a spacetime curvature. What does curvature mean? Okay, this would be quite technical, so let me just point out that there are different ways in which one could measure spacetime's curvature, and one of them is the so-called Ricci curvature, which again is also a function in the same way that L is, and it also depends on the point P and the spacetime direction B, and we will use it. Okay, so now that we have covered the geometric foundations, let us move to the applications. And I will cover really different types of applications. I will start with some related to signal propagations and wave propagations, and then I will move to the cosmological applications after that. But starting with propagation, anisotropic propagation. Okay, so Finsler spacetimes inherently contain anisotropy, and this allows for anisotropic propagations of waves, say. So waves that do not propagate the same in different directions. How do we study propagation? Well, we start at the same point as in the classical case, by Huygens principle, which says that when one has a wave, each point of the wavefront at a certain time will act as the source of some secondary waves, so that at a later time, the new wavefront will be the envelope of these secondary waves. Formally, the equation would be this, so that the front at a second time will be, take the front at the initial time, compute what is called the causal feature, takes its boundary, and evaluate at time t1. So you can see this paper by Cavaloyes, Pendas-Recondo, and Sanchez for the details, but the idea is this. Take an initial state of your wave, which will be represented by this black line, and take the wavefront S. Now evolve everything in time. The evolution here in this picture is vertical, so things evolve in time. And we take this evolution, as I said here, and we take the boundary. Why do we take the boundary? Well, because we take the points of our wavefront to evolve, say, as the maximum possible speed. So the speed of light, or really the maximum possible speed of the wave in the medium. And this maximum speed condition means that each point will evolve really by, at each point here, going always tangent to the boundary of these small cones. So this condition of always being tangent, always being tangent, always being tangent, always being at the boundary of the cones, this is what will mean to take the boundary of the causal feature of our evolution. And that's why this distribution of cones, which is determined by the Lorentz-Finsler metric, is really what drives the evolution. So for the causal propagation, everything is encoded in the cones, and the cones are given by the Lorentz-Finsler function. In particular, we can model, for example, not just any type of wave. We could try to model, for example, the wavefront of a wildfire. And here I will say that there was previous models of wildfires, and they were first Finslerized by Mark Borsen, and later by Cavaloyes, Pendas-Recondo, and Sanchez. And the idea here is that because of the Finslerian geometry, we have much more freedom. So there are many improvements with respect to the previous models. For example, in the propagation shape, the previous models only allowed essentially for ellipses, but now with Finsler geometry, one allows for any convex curve as the propagation shape of the wildfire. Secondly, now this is done solving ODEs instead of PDEs, which of course computationally is much more simple and more efficient. And third, also an important point is that now, thanks to Finsler geometry, one has many tools to study the so-called cut points. Now, what is a cut point? Well, a cut point is a situation of this type where you have a wildfire and at the beginning it starts propagating in divergent directions, but it may happen that at a later time, the different propagation directions will converge again at a point like this. This is a so-called cut point. Why is this important? Well, it is important because in real life, if the firefighters are fighting this wildfire, it is very important to avoid that they get stuck at points like this, because if they get inside this region, eventually they will be enclosed in this region by the cut point, and this will be very dangerous for their lives. So, of course, from a very practical viewpoint, it is hugely important to try to predict these cut points and, if possible, avoid them in the position of the firefighters. But luckily, cut points are a very classical topic in Finsler geometry. So the textbooks on Finsler geometry already give many tools, many theoretical tools to study the cut points. And now these tools can be implemented in the wildfire model. And in this way, one hopes to be able to predict them and to avoid them, which, as I said, yeah, it's clear that it's hugely important for fighting a wildfire in practice. So many improvements with respect to classical models in the end by means of a new geometry, which I think is surprising. And at the very least, it was quite surprising for the authors when this began. Now I move to the so-called, what we could call the cosmological applications. And I will start, for example, with the study of dark matter. Now, what is dark matter classically? Well, the point is that general relativity is a very successful theory, but still there are many well-known anomalies with respect to it. For example, in spiral galaxies, one finds that the other parts of the arms rotate faster than they should. Well, they rotate faster than they should, provided that visible matter is really all that there is. And this is very difficult to explain with classical gravity or general relativity. Well, there are many more phenomena of this type and similar types, but I will not enter into them in order to not complicate things. And then what's the usual explanation for this? The usual explanation is, okay, then the matter that we see cannot be all of the matter. And that's why people postulate the existence of dark matter. But in the end, one finds that this dark matter, this unobserved dark matters, makes up 27% of the universe. And because of things like this explanation may be just a bit unsatisfactory, at least to the taste of some people. Is there any alternative explanation rather than postulating the existence of more matter that we do not see? Well, the alternative explanation is that we do not understand the laws of gravity well. There are a couple approaches in this direction. One is the so-called modified Newtonian dynamics, or MOND, or another approach is to just modify the laws of Einstein's general relativity. Finslerian relativity would be in this type of approach. It's a modification of the laws of general relativity. And in fact, there has been works in this direction. For example, these authors here claim that they can recover MOND as the quote-unquote Newtonian approximations to Finsler spacetimes. And in this way, this modified Newtonian dynamics model, which probably was a bit ad hoc before, now has a deeper explanation in terms of Finsler geometry. And if this is true, if one believes in Finsler geometry and subsequently in this model, then there is no need to introduce dark matter anymore. Okay? In this way, the anomalies would be explained purely by geometric effects. by the effects of a new geometry, of a Finsler geometry. There is no need to introduce dark matter now, which, as I said, to some people can be much more satisfactory. There is also the issue of dark energy. And here the thing is that we observe that our universe is expanding, but not only expanding, it is expanding acceleratedly. But basic general relativity does not cover this possibility. Now, again, what's the usual explanation for this fact? It is to postulate the existence of some extra energy in the universe that we do not really observe, the existence of so-called dark energy. And here, the situation may be even worse, because one finds out that dark energy in the end should make up for 68% of the universe, which, again, the same problem. This may be seen to be quite advanced philosophically. Again, the same alternative explanation as before. Maybe there is no such dark energy, and maybe we just do not understand the laws of gravity well. So can we approach the problem with Finsler geometry? In other words, can a Finslerian modification of relativity do away with the need for dark energy? Well, for example, the same authors as before claim that this is possible in one paper, but here in this problem we have even more approaches. But in order to understand them, these further proposals, we will need to start to pay attention to the dynamics of the gravitational field. What's really the law that governs the gravitational field in this Finslerian theory? Well, first of all, in the simpler theory, the gravitational field is completely determined by the metric L, and for the law that governs it, one postulates a variational principle. So to make this simple, one postulates that the true gravitational field is the one that makes the least action, one that minimizes more or less this action. What's the answer? Well, the action is just the total Ricci curvature. So one takes the Ricci curvature function, which depends on the point and the velocity, and one integrates it everywhere, and this is the action. And one postulates that the true gravitational field would be the one that in some sense minimizes this action. And this gives a PDE for the gravitational field, which one can study, and this is the dynamics. This was started by Pfeiffer et al. Around the year 2012, and this is really a generalization of classical relativity, in the sense that this is directly generalizing the Einstein-Given axiom from classical relativity. So yeah, it's a straightforward generalization of the classical approach. Now, the thing about this axiom that I have shown you is that it describes only gravity. But what about the rest of matter and energy on a spacetime? Let's group it on a field C on a spacetime. Well, in order to describe this, one has to write a total axiom, which is the coupling of the gravitational axiom and some other matter axiom. And here is where we have, again, a lot of freedom to build models. There is a remarkable thing. If one builds this concrete model here, where this phi is the distribution function of some kinetic gas on spacetime, if one does this, one realizes, as Hoffman, Pfeiffer, and Boykud did, that one gets an improved description of matter as opposed to classical relativity, in the sense that this kinetic gas model is finer than the traditional model. Why? Because the traditional model did some averaging over the relative velocities of the individual bodies. And now this new model doesn't do this averaging and accounts for all these individual velocities. Now there is some work in progress here, because the authors hypothesize that this refined description of the matter, which, again, the important point, this is only possible in Finsler geometry. These authors hypothesize that this refined description may induce this accelerated expansion of the universe. So again, let us recapitulate. If this is true, then there would be no need for dark energy, and then the observed effect would be explained only in terms of geometric effects of this new Finsler geometry. And this, together with the previous application, this illustrates, these are just a couple examples of the potential advantages of Finsler geometry in cosmology. But here, let us illustrate the idea with a picture. The idea here is that we have a picture of the expansion of the universe, and here inside the universe, we have the individual bodies, particles, which you may think of them as gas particles. And the thing here is that traditionally, all the relative motions of these particles were averaged and the information was lost. But now in Finsler geometry, all the individual motions of these particles here are taken into account. And in this way, the hope of different authors is that these individual bodies may drive, just by the equations, may drive an expansion of the universe in an accelerated way. So in this new model, thanks to Finsler geometry, the individual motions may influence spacetime geometry and drive an expansion, an accelerated expansion without having to introduce dark energy. Okay, so after I have covered some of the main applications, let me tell you briefly just a bit of what I did in my PhD thesis. I did a couple of things related to this, but I will explain them briefly just to illustrate the many possible directions that one has in Finsler geometry. And okay, the starting point of my thesis is that this metric, this invariant L, allows for measurements of time, space, and other things. But really, if one is more precise than before, the gravitational field is given by another object, which is encoded in these so-called connection coefficients. They are functions with two indices of this type. The details don't matter, but the point is to ask, must really be everything a function of L alone? In other words, must this gravitational field depend on the metric on a very precise way, which is called the canonical connection? The answer is, of course, not necessarily. I mean, this was just the simplest possibility, but there is even more freedom. There are more possibilities. One can take the metric and the gravitational field to be independent and defend, again, basically the same action as before. And in this new theory, one has even more freedom, as I said. Now, what's the thing? The thing is that classically, the two theories, only the metric or the metric and the connection, classically, the two theories coincide, because classically, they are just the Hilbert or the Palatini formulation of Einstein's general relativity. But in Finsler, they do not coincide, and as I said before, one finds even more possibilities, which we studied in the main paper of my thesis, together with my advisors, Miguel Ángel Jabaloyes and Miguel Sánchez. But we did more than this, because besides analyzing the solutions of this new theory, we clarified some issues with this, some mathematical issues with these connections that were a bit unclear before in this other paper. We also studied the matter side, because we came up with this idea of this anisotropic stress energy tensor, which can be used to try to build a general coupling of Finsler gravity with matter in this other article. And we also found some applications to mathematical curvature problems in pure Finsler geometry. So these ideas that I have briefly covered can be used, can be exploited even to address some very pure mathematical problems. So, well, in sum, the point is that Finsler spacetimes and their applications form quite a young, actually, and very vibrant field. And as you can see here, there are many research avenues that one can take, and there are many avenues to explore and new things to discover. So with this, I finish my presentation. Here are the main references, but for anyone who is interested in some particular point, I can point it them to you more precisely, because there are many of them. And with this, I really finish, and I thank you all for your attention. Thank you very much.